Today we're going to start a new chapter, chapter 12, intermolecular forces and liquids and solids. Today it's just going to be the intermolecular forces part. There are 4 or 5 different types of intermolecular forces, and these intermolecular forces also help us determine whether something has a higher boiling temperature, higher freezing temperature, higher viscosity, and there's a bunch of other terms. I'm losing it right now, but it's in the notes. It's going to come up about because something has higher intermolecular forces, this molecule will have these properties. Okay. And from knowing about intermolecular forces, you can also determine whether chemical A will boil at a higher temperature than chemical B, even though you don't know what the actual boiling temperature is. But because you know the forces that hold them together are stronger or weaker, you can determine that A or B has a higher boiling temperature compared to each other. Okay, so that's a general idea of what we're going to be doing in chapter 12 about intermolecular forces. So let's get started what intermolecular forces versus something like intramolecular forces are. So intermolecular, actually even before that, let's start with the term phase. A phase is a homogeneous part of a system that is in contact with other parts of the system but separated by a well-defined boundary. For instance, if you have iced tea or ice water, okay, this is just ice water, you can have the solid phase, you can have a liquid phase, and it's a well-defined boundary. You know exactly where the ice part is and where the liquid is. It's not it's not a guess like, oh, I'm not really sure where's ice and where's liquid. It's pretty clear. It's a well-defined boundary where the solid and the liquid phase are. There are some properties of solid liquid gases that we know. Of course, you have gases that are takes the shapes and volume of its container. Highly compressible. The movement is, however, once ago, very free motion. Liquids have a definite volume, takes the shape of its container. It's only slightly compressible. Liquids, if you had a gallon or a liter of water, you can't really squeeze it. I mean, it squeezes a touch. I don't want to say none at all, only slightly. Okay, can you compress a liquid? You can't squeeze a liquid into a smaller volume in general. But the molecules can move and they slide past each other. In a solid, they have a definite volume, definite shape, and they're virtually incompressible. I'm not talking about say, oh, but I have a piece of bread and I could squish it. Okay, that's you're squishing out the air, the gas. Okay, um, but once you have some solid like a rock, you cannot compress a rock in general. Okay, it's virtually incompressible. In case you're like, but you can squeeze a mountain down like under high pressure. Okay, it's a little bit, but not much. In general, it's virtually incompressible. The motion of molecules, they vibrate about in fixed position. So just starting with a couple of definitions. First, starting with phase. So the difference between intermolecular forces and intramolecular forces. Intermolecular forces are forces between molecules, and intramolecular forces holds the molecules together. Think intermolecular like if I'm taking an international flight. Well, no one's going anywhere right now. If you're taking an international flight, you're going between nations. Between, okay? The Intercontinental Railroad, it's not really between continents, but anyway, between states, okay? Uh, just realize that the Intercontinental Railroad between across the United States is not across. It's okay. It's within the continent. Okay, but I didn't name that one. Okay, intramolecular forces is atoms that hold atoms together within the molecule. It's kind of like you might say domestic within the atom. So if you say water, H2O, the force between hydrogen and oxygen, that is an intramolecular. That's within the water molecule. But what's the force that holds together a water molecule and another water molecule? There are two separate molecules, water molecule and a separate water molecule. There is some force that holds it together. That's why they make drops. What are the forces that hold it together? The forces, attractive forces between two separate molecules is an intermolecular force. Intermolecular forces, attractive forces between molecules. Usually there will be attractive forces. I'm not saying there is not any repulsion, but in general, there are going to be attractive forces. So if we're talking about force to vaporize a mole of water, it's an intermolecular force. Why? Because the forces that holds it as a liquid versus a gas, the gas molecules, those molecules are far apart from each other. In the liquid, they are much closer to bonded together. So you're breaking apart intermolecular forces. But if you're breaking apart the hydrogen-oxygen bonds in water, then it's no longer water. It's something else. That's an intramolecular force. Intramolecular forces are within the molecule, breaking apart bonds. Intermolecular forces, usually we're talking about changing states of matter, solid, liquid, gas. Okay, and we're just talking about solid, liquid, gas. Let's not get into what about plasmas. Okay, yeah, we know it exists. What about if you ever even heard of a Bose-Einstein condensate, another state of matter? Yeah, well, whatever. We're talking about the main states of matter, solid, liquid, gases. So we're talking about changing states of matters. We're talking about intermolecular forces. You're not changing the molecule. Once you break bonds, now it's no longer the same molecule. That's an intramolecular force. So in general, intermolecular forces are much weaker than intramolecular forces. So that's in general, but most intermolecular forces are much weaker than intramolecular forces. What are some measures of intermolecular forces? Boiling point, melting point. When you boil something, you turn something into a liquid to a gas. Again, you're changing the state of matter. Melting, like melting ice. You're turning it from a solid to a liquid. You will be melting. And that is a measure of an intermolecular force. Forces that holds a solid together. Heat of vaporization. We'll see that term, heat of fusion. The amount of energy that it takes such that you can start to turn it into a gas. Heat of vaporization, heat of fusion. These terms will come up a little bit later, but notice they are all related to changing mostly states of matter or our phases, okay, that we had in the last slide. So, and heat of sublimation. You might have heard the term sublimation before. It is going to come up again later on, but just a preview preface for it right now. Sublimation is turning a solid into a gas without ever becoming a liquid. Examples of solid into a gas without ever becoming a liquid would be dry ice. Okay, dry ice turns from a solid state into a liquid state without ever becoming a gas. Sorry, solid to a gas state without ever becoming a liquid. I said that wrong. So solid into gas without ever becoming a liquid. Other examples of that is why sometimes your ice cubes in the freezer seem like they're shrinking. It's going through sublimation. It goes from a solid state into a gas state without ever becoming a liquid, and your ice cubes look like they shrink in your freezer if you don't use them for a while. Okay, let's get to, I believe there's going to be 4 or 5 main types of intermolecular forces. The first one is called a dipole-dipole force. And dipole-dipole forces are attractive forces between polar molecules. Okay, I didn't really get to it right now. There's going to be a separate one about video about how do I know a molecule is polar. But quick thing in general, polar molecules is when you have a molecule that has more electrons on one side than another. We talked about polar bonds already. But when a molecule is polar, that means the electrons are more on one side of the molecule than the other side of the molecule. So one side, if the electrons are more on one side, that side is obviously what we say is a negative side. And relatively speaking, the other side is a positive side. So one side of the molecule it has the electrons, the other side doesn't, relatively speaking. That is a polar molecule. So let's say this is a polar molecule. It's kind of like a negative, positive, negative, positive. Well, guess what? These negative and positives attract. It's like having a whole bunch of little magnets. Okay? Polar molecules, because they have attractive forces because of these opposite charges. When you have little magnets, they attract each other using what's called dipole-dipole forces. Dipole-dipole forces are attractive forces between polar molecules. And we'll talk about, again, a separate one about how do I know something is polar. A polar molecule, one side, the electrons are more on one side of the molecule than the other. Another type of intermolecular force is an ion-dipole force. That is a polar molecule and an ion. An ion, something positive or negative, and something that is polar, where you have something positive, you have something negative, you have something negative, and you have a part that's positive. They attract. And in a way, that's kind of why salt dissolves in water. The attraction between water, which, by the way, is a polar molecule. Water is a polar molecule. The attraction between water and sodium is greater than sodium and chlorine. So it breaks it apart. So that's why water dissolves something. And I believe that's coming up anyways. So in general, when you talk about ion-dipole forces, attraction between ions and polar, the stronger the ion, the stronger the interaction. This is a water molecule, Positive 1, positive 2. The stronger the charge, the stronger the interaction. The weaker the charge, relatively speaking, the weaker the interaction. Stronger bonds, or stronger charge, stronger interaction. Weaker charge, weaker interaction. Okay, next one is called dispersion. Dispersion forces. Attractive forces that arise as a result of a temporary dipole induced in atoms or molecules. Okay, this is a little bit more complicated to explain, and I usually like to give an analogy. This is only analogy. This is not a real life situation. Okay, let's say you have there's electrons and it's in here and it's equally spread out, so it's actually not polar. Okay, the electrons are equally spread out all along here. And so, and because it's not polar, you're like, well, if it's not polar and non-polar, these things will not attract each other. Unlike way back here, when we said polar and polar things attract, what if it's not polar, meaning the electrons are equally spread out? Then you would say it's not attractive. Well, the thing is, there's always going to be a little bit of attraction called dispersion forces. So let's say it's equally spread out, and let's say this is me coming along, or some positive cation, or it could be negative anion comes along. What happens if you had some positive cation? It attracts electrons towards it because negative attracts positive. And for temporarily, it seems like it's polar. The negative electrons are on this side because it's attracted to positive cation. So temporarily, it looks like it's polar. Okay, here's my analogy again. It's just an example. Let's say there was a restaurant. Okay, pretend there's restaurants available, and everyone's single and it's all equally mixed up genders. Okay, it's equally spread out. It's not like all the men or all the women are on one side or another. Again, this is just an analogy of what I'm saying. And let's say I come along, and being the supermodel that I am, okay, and I'm positively charged, all the negatively charged people, all the opposite whatever, people are attracted to me, all run towards me because I'm such an amazing supermodel. And people just are attracted to me. Well, that restaurant, which was all equally mixed up, male, female, is not temporarily because all the negative charges are attracted to me. And relatively speaking, the other charges, they're just there. Okay, so temporarily, it looks like it's polar, but it's not really. The moment this cation's gone, then it's like the moment I leave that restaurant area, then that restaurant goes back to how it was. It's equally mixed up again. Okay, but temporarily, it induces a dipole. It makes it look like it's polar. So if you had something that is polar, you put it next to something that is not polar, it's going to make it temporarily like it's polar. So negative attract a positive. So ion-induced dipole, dipole-induced dipole, These forces are called dispersion forces. These are actually the weakest of our intermolecular forces. And we're going to get to a list of, hey, what are the strong intermolecular forces? Which are the weak intermolecular forces? Dispersion forces are actually some of the weakest. And all molecules actually will have dispersion forces. Okay, so dispersion forces continue. Polarizability, the ease in which the electron distribution of atom of or molecule can be distorted. So how easy is it for me to make that restaurant that was all equally mixed up, make it something like it's polar, where all the whatever gender are on one side because they're all attracted to me. Okay, again, that was just an analogy. Well, it increases with greater number of electrons. The more electrons it is, then the more likely it'll appear to be polar. The more diffuse the electron clouds, also, dispersion forces usually increase with increasing molar mass. Here are 1, 2, 3, 4, 5 compounds. Notice as I increase molar mass, CH4, CF, molar mass from the periodic table, 1 carbon, 4 hydrogens, 1 carbon, 4 fluorines, 1 carbon, 4 chlorines, 4 bromines, 4 iodines. It increases molar mass going down that way. Notice melting point also increases. So if you have molecules that are all dispersion forces only, then the higher the higher the molar mass in general, you're going to have higher the melting point. So increase molar mass, you're going to increase melting point. Okay, so what are type of intermolecular forces that are going to occur in each of these? HBr. HBr is a polar molecule, and if it's polar, it will have dipole-dipole forces, and all molecules will have dispersion forces. All molecules will always have dispersion forces. Next thing, CH4, methane. If you drew the Lewis dot structure, you'll see that, hey, it's equally, the hydrogens are all equally all around it, meaning it's going to be nonpolar. And if it's nonpolar, it will not have dipole-dipole forces. It only has dispersion forces. Last one, SO2, sulfur dioxide. Drawing the Lewis dot structure looks like this. You'll see because it has that lone pair on it, this molecule is bent. And because it is bent, this molecule will be polar. And because it's polar, it will have dipole-dipole forces. And like all molecules, it will have dispersion forces. So this is the beginning of intermolecular forces. And we're going to continue on about some properties of some of these intermolecular forces.